Hello, everybody. Today we will be solving problem 22 of the 2021 USMCA Championship. The problem reads, let ABC be a triangle with AB equals 20, AC equals 21, and angle BAC is 90 degrees. Suppose that gamma 1 is the unique circle centered at B and passing through A, and gamma 2 is the unique circle centered at C and passing through A. Points E and F are selected on gamma 1 and gamma 2 respectively, such that E, A, and F are collinear in that order. The tangent to gamma 1 at E and the tangent to gamma 2 at F intersect at P. Given that PA is perpendicular to BC, compute the area of PBC. All right, so first of all, I've drawn the intersection of PA and BC. They intersect at D and this right angle over here. Right, we have that, and now I'm going to claim, first of all, that claim is that P lies on the radical axis of the two circles. And how am I going to prove this? I'm going to take these two circles and I'm just going to draw them out right here. And I'm going to start out by proving that the line joining the two centers and the radical axis, which is the segment connecting these 2 points, are perpendicular to each other. And that's not hard to prove because what do you have but some radii? We're going to call this one, well, let's just call it 20. This one's 20. This length is 21. This length is 21. So you see what we have here is actually a kite, and it's a property of kites, well-known property of kites, that the diagonals are perpendicular. So BC is perpendicular to this radical axis over here. But you'll notice that this is A and this is D, the point of perpendicularity. And if you were to extend this line segment DA out further, you're given that since PA is perpendicular to BC, P is on this segment. So therefore P is on the radical axis. And what does that mean? It means that the power of P with respect to the two circles are equal to each other. And that's going to mean that PE equals PF, right? Since the power of P with respect to the first circle is PE squared. The power of P with respect to the second circle is PF squared, right? And they're equal because P is on the radical axis. So we have PE is equal to PF. Okay, now I'm going to do a bit of angle chasing, and what I'm going to do is I'm going to claim that angle EPF is 90 degrees. Okay. So first, let me mark a bunch of angles as right angles. This one over here is a right angle. Since it's 180 minus angle BAC, which we know to be right from the problem statement. We also know this angle is a right angle because PF is tangent to the circle, which has center C. And similarly, this is 90-degree angle. Right? Okay, so now what I'm going to do is I'm going to call this angle X. Angle CAF is X and angle CFA is X because triangle ACF over here is isosceles with CA equals to CF. They're both radii. Right, and since this angle over here is 90 degrees, angle BAC, this angle over here is 90 minus X. Angle BAE is 90 minus X, and this angle over here is 90 minus X as well. Okay, and what does that mean? It means that this angle is 180 minus X, which is 180 minus 2X. This is from triangle CAF. And this angle over here is 2x because triangle BAE needs to have angles that add up to 180 degrees. Okay, so that angle is 2x. This angle is 180 minus 2x. We're given that this angle is 90 degrees. This angle is 90 degrees. So take a look at this quadrilateral over here. I'll do it in a different color. This quadrilateral over here has two 90-degree angles. The third angle is 180 minus 2x. So this angle over here is 2x. So this angle over here is 180 minus 2x. Okay, now take a look at this quadrilateral over here. This one over here. This angle plus this angle is 180 minus 2x plus 2x is 180 degrees. This angle is right. So this angle over here must be right for the four angles to be 360 degrees. So what do we have but angle EPF equals 90 degrees. But remember, we already had PE is equal to PF. So now let me get rid of a bunch of stuff that's cluttering up this diagram that we don't need anymore. So since we have angle EPF is equal to 90 degrees and PE is equal to PF, we have, what do we have but a 45, 45, 90 triangle, isosceles right triangle. This angle is 45 degrees. This angle is 45 degrees. Okay. Now, when I draw CF, we already knew that this angle was a 90-degree angle, which means this is 45. But this is also 45 because we're given triangle CAF was isosceles, so these two angles were equal to each other. Hence, this angle is 90-degree angles, and CAF is a 45, 45, 90 triangle. Similarly, if we draw in side length BE, what do we have but, since this was a right angle, this is also 45 degrees. So this is 45 degrees since this angle is equal to that angle, since this triangle is an isosceles triangle. So this is also a right angle. Right? Okay, so what can we do now? I'm going to extend CA over here. And we know this is a right angle because it's complementary of this angle. This angle is a right angle, this angle is a right angle. So finally, this angle must be a right angle. And remember, back in our problem statement, we stated that AB is 20. So if we're going to call this point, let's say G, we have BAGE is a rectangle. Actually, it's a square because this has, the BE is 20 as well. So EG is 20. Okay, now take a look at CFPG, right? Given this is a right angle, this one over here is a right angle, this one's a right angle. This is also a rectangle. And remember, since the circle centered at C has radius 21 because AC is 21, since this is a rectangle, GP is 21, right? So PE is 41, that's 20 plus 21. And so PF is also equal to 41 since PE is equal to PF. Okay, so now let's stop for a moment and take a look at triangle PEF, which is what we're really focusing on. And I'm also going to draw point A. We've learned a lot about this triangle PEF. We've learned that it's an isosceles right triangle, and that this side length is 41 and this side length is 41. Okay, also note that BE is 20, BA is 20. So since this is a 45, 45, 90 triangle, AE is 20 square root of 2. And similarly, AF is 21 square root of 2 because ACF is a 45, 45, 90 triangle. So now we can find PA using Stewart's theorem. And remember, if you don't remember what Stewart's theorem is, it's if you have a bunch of lengths, you want to find this CV and D, and then we're going to label these lengths MN, and this whole side is A, then this one is length B, this one is length C. Stewart's theorem says that MAN plus DAD equals BMB plus CNC. You can remember this with the mnemonic, a man and his dad put a bomb in the sink. What we're going to do is we're going to apply this theorem to this triangle. We're going to call this one D. We get by Stewart's theorem 20 root 2, 21 root 2 times 41 root 2 plus D squared 41 root 2 equals BMB plus CNC. 41 squared times 21 root 2 plus 41 squared times 20 root 2. Okay, now I'm going to give myself a tiny bit more space by getting rid of this stuff. We have these two terms have a product of, that's 420 times 2, which is 840 times 41, 41 root 2 plus D squared times 41 root 2 equals this right-hand side. We can factor out a 41 squared times 21 root 2 plus 20 root 2 is 41 root 2 as well. So we can cancel 41 root 2 out from both sides. You get D squared equals 41 squared minus 840. This is going to be 841. So D squared is 841. If you take the square root of 841, you get 29. So PA is 29. Now we're almost done. We just need to find DA and then take base times height a bunch. Right? And okay, now we take a look at triangle ABC, and you might have already recognized it as a 20-21-29 triangle. Basically, you have, if you have a right triangle with leg lengths 20 and 21, the hypotenuse is 29. You can prove this by Pythagorean theorem. Right, so BC is 29. Okay, then we have AD. We want to find AD, and that's not hard to do. You could do it using similar triangles, or you could realize that the area of ABC is 20 times 21 over 2, half the product of the legs. It's also equal to base times height this way, where BC is the base. So 29 times AD over 2. You can get AD equals 20 times 21 over 29. All right, now we want to find this area, the area of PBC. You can realize that since PAD collinear perpendicular to BC, you have this area is equal to half times BC times PD. This is going to be equal to half times, well, BC is 29 and PD is going to be PA plus 80. That's going to be 29 plus 20 times 21 over 29. And once you compute that out, you get half of 841 plus 420, which is 1,261 over 2. That is the area of PBC. So thanks for watching, and I will see you next time.